Welcome to our exploration of magnetic force on moving charges. When charged particles move through magnetic fields, they experience a force that can dramatically change their path. This fundamental concept explains everything from how electric motors work to how cosmic particles are deflected by Earth's magnetic field. Understanding this force is crucial for grasping the behavior of charged particles in magnetic environments. The magnetic force on a moving charge is given by the simple yet powerful formula F equals qvB here. F represents the magnetic force measured in newtons, Q is the electric charge of the particle measured in coulombs, and V represents the velocity of the charge in meters per second. This formula shows us that the magnetic force depends on three key factors: how much charge the particle carries, how fast it's moving, and the strength of the magnetic field it encounters. Let's examine each component of our formula in detail. The variable Q represents the electric charge, which is the fundamental property that determines how strongly a particle interacts with electric and magnetic fields. The velocity V tells us both how fast and in what direction the particle is moving. Finally, B represents the magnetic field strength, measured in units called Tesla. The stronger the magnetic field, the greater the force on our moving charge. One of the most important aspects of magnetic force is its direction. The force is always perpendicular to both the particle's velocity and the magnetic field. We use the right-hand rule to determine this direction. Point your index finger in the direction of velocity, your middle finger in the direction of the magnetic field, and your thumb will point in the direction of the force. This three-dimensional relationship is what makes magnetic force so unique and powerful. The complete formula for magnetic force is F equals qvB sine theta, where theta is the angle between the velocity and magnetic field vectors. When the particle moves perpendicular to the field, theta equals 90 degrees, and sine of 90 degrees equals 1, giving us maximum force. However, when the particle moves parallel to the field, theta equals 0 degrees, and sine of 0 equals 0, resulting in no magnetic force at all. Here's a fascinating property of magnetic force. It's always perpendicular to the particle's velocity. This means the force changes the particle's direction, but never its speed. Since the force does no work on the particle, the kinetic energy remains constant throughout the motion. This is fundamentally different from other forces that can speed up or slow down particles. Let's solve a practical example. An electron moves perpendicular to a magnetic field. Given that the charge is 1.6 times 10 to the negative 19th coulombs, velocity is 2 times 10 to the 6th meters per second, and magnetic field strength is 0.5 Tesla, we can calculate the force. Using F equals qvB, we get 1.6 times 10 to the negative 13th newtons. Now let's consider a more complex scenario where the particle doesn't move perpendicular to the field. A proton moves at 30 degrees to a magnetic field. With charge 1.6 times 10 to the negative 19th coulombs, velocity 5 times 10 to the 5th meters per second, and field strength 0.8 Tesla, we use the complete formula. The sine of 30 degrees is 0.5, giving us a final force of 3.2 times 10 to the negative 14th newtons. When a charged particle enters a uniform magnetic field perpendicular to the field lines, something remarkable happens. The perpendicular magnetic force acts as a centripetal force, causing the particle to follow a circular path. The particle maintains constant speed while continuously changing direction, creating a perfect circular trajectory. This principle is used in many applications, from particle accelerators to mass spectrometers. Let's summarize the essential points about magnetic force on moving charges. The force follows the formula F equals qvB sine theta, showing it's proportional to charge, velocity, and magnetic field strength. The force magnitude depends on the angle between velocity and field vectors. Most importantly, the force is always perpendicular to velocity, which creates circular motion when particles enter magnetic fields perpendicularly. This fundamental principle governs the behavior of charged particles in magnetic environments throughout the universe.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.